All right, we are still in section 3.2. Rolle's theorem is named for a Frenchman, right, mathematician, and it has a lot of things in common with the mean value theorem. So we study one theorem and the mean value theorem first, and then because this is so closely related to it, it makes a lot of sense to do it in the same section. So because we have a little bit of experience with the mean value theorem, we're actually going to write Rolle's theorem out first and then look at what it means graphically and how it's the same and how it's different. So it starts off very much the same. If f is continuous on the closed interval a to b, brackets, not parentheses, and differential, we're going to do a comma here. Differentiable, because we are making a list of 3. Differentiable on the open interval a to b. And, here's what's new, f of a equals f of b. Then there exists a value c in AB such that f prime of c equals, and I'm going to leave a little cliffhanger here. So, whoops, what goes in this yellow space? What must f prime equal? So we're going to take a look at this graphically and see if we can figure it out. So let's go with just a random function here. Nothing too fancy about it. Let's just draw something that looks like this. And then, of course, when we choose, let's say this is A, and let's say B is like here. Now, I'm very specifically choosing these 2 points, and you'll see why. So, again, like before, think about our checkboxes. This function is continuous, and it's differentiable on this interval a to b. Now we have to check and see if f of a equals f of b, right? And that's the new thing. That's the caveat here with the mean value theorem. So let's kind of put points. Again, I have specifically chosen these points, so if you just kind of graph this and it's not exactly like mine, you'll kind of notice a difference. So when I figure out what the y value is at A and the y value is at B, it does look, right? Then I generated this graph so that these 2 values are exactly the same, okay? So if I look at these 2 values here with f of A, right, and f of B being the exact same y value, ugh, so bad at drawing. What do we think that this theorem says? What goes in that yellow space up here, right? If we think that it has a lot in common with the mean value theorem and f of a equals f of b, the average rate of change is what, right? It's obviously 0. So we are saying that there is specifically a point where the derivative has to equal 0 if the average rate of change over this interval is 0. And that makes sense, right? Because, all right, we're going to have possibly a point here. That's a c value. We have this minimum here. That's a different c value. Properness would probably be to name them 1 and 2. Okay, but we do have, if we think about before, right, we were using orange and purple, orange line, 2 purple lines that are tangent and parallel to it, right? That's how we come up with the slope equaling 0. Okay, so that's the conclusion of this, is that if you have an average rate of change equal to 0, a flat secant line, then there has to be at least one place where the tangent line is 0, which of course is represented by the derivative. And to me, this is really lame that this guy gets this theorem named after him for it not being that intent, it just seems to me like one example of the mean value theorem, but it gets to be named after him. I don't know why. So let's try example 1. There's only 2 examples here today, so it's going to be pretty quick. We're going to try to find the value of c, guaranteed by Rolle's theorem, for sine of x over pi halves to 3 pi halves. Okay? So let's check our conditions first, right? Go through the check boxes. Is sine of x continuous on that interval? Yes, right? Because sine, right, is just a nice little periodic function. It goes on forever. Okay? Pi halves and 3 pi halves would be, at these 2 parts of this periodic function. Is it differentiable? Yes. Right? There's no cusps, no corners, no holes, no asymptotes, nothing that would cause it to not be differentiable. And then now, is f of pi halves equal to f of 3 pi halves? Right? So f of pi halves, we know, should be 1. And f of 3 pi halves, right, if you plug it in or if you know your unit circle, that actually is negative 1. So no, right? The Rolle's theorem does not exist on this interval. Okay, and so we have to say that since we can't find the value of c, we have to eloquently state why we cannot do it. Okay, Rolle's theorem does not apply because f of pi halves does not equal f of 3 pi halves. Okay? Now, what is not appropriate to say, we do not want to do something like this. We don't want to say Rolle's theorem does not apply because f of A does not equal f of B, right? If it's all about scoring points for the judges someday, this is too vague of a statement, and it doesn't show that you understand what the value of A is and what the value of B is. So we don't ever want to use that. We want to use the context of the question to make our justification. So that's why we're going to roll with f of pi halves not equal to 3 pi halves, and then that's enough. Okay? All right, last one. Find the value of c guaranteed by Rolle's theorem, where f of x is sine squared x plus cosine x all over 0 to 2 pi. So same as before. Make the checklist. Okay. Is this function continuous? Well, we know that it is because sine is continuous, cosine is continuous, and all we're doing is adding them together. If we were like dividing them, right, that would cause a different issue. But since individually they're continuous, when you combine them, they are as well. Is it differentiable? Yes, same reason as example 1. And now we have to ask ourselves, does f of 0 equal f of 2 pi? So let's plug in and calculate f of 0. That's sine squared of 0 plus cosine of 0, which is 0 squared plus 1, which equals 1. And then the second value, right, is f of 2 pi. So is sine squared of 2 pi plus cosine of 2 pi, also 1. Let's check it out. So sine of 2 pi we know is 0. Cosine of 2 pi is also 1, OMG. So we have 2 y values that are samesies. So we can check this box off and continue with our work. Now that we have checked the box off, we're going to go ahead, take the derivative, and set it equal to 0. I know automatically my average rate of change is 0, right? So, because this is Rolle's theorem specifically, so I can just go ahead, take my derivative, right? So, derivative of sine squared, this is a composite term, right? So it's got to be 2 sine x times cosine x. That's the chain rule. And then not plus, but minus sine of x for the second term, right? Derivative of cosine of x is just negative sine. So when I put those two together and try to set them equal to each other, this seems to work out nicely because probably factoring is the only way we're going to be able to solve this, right? So let's take out a sine of x. I'll be left with 2 cosine x minus 1 equal to 0. Let's set sine of x equal to 0. Let's set 2 cosine x minus 1 equal to 0. And then let's think about sine in this interval, right? 0 to 2 pi. I know I can't pick these endpoints, so only pi, that value in the middle, is going to be the only solution that I want for this work. Okay, so exclude those endpoints. Now the other one, we got to do a little bit of more math here. So 2 cosine x equals 1, cosine x equals 1/2. And now let's think about where cosine equals 1/2, right? So cosine, remember, is our x measurement here. Oh, that's negative 1/2, moron. And this triangle here, depending on how good you know your unit circle, right? This is 60 degrees, right? And what's this guy? 300 degrees. Turn those back into radians, right? So our two values are pi thirds and 5 pi thirds. Okay, so we've got three options here, right? And actually all three of them are solutions. I've got pi thirds, and 5 pi thirds as my solution set. So that is what I come up with. Now these examples have only been trig functions. This applies to quotients, exponentials, logarithms, right? Product rules, quotient rules, chain rules, all the other things we've been doing in calculus derivative wise. So, you know, it's a good little run for your money about those calculations that you can do with the derivative.